topic.
Thank you, Barbara, for the nice introduction. Thank you also for using a headshot from 30 years ago. That was my first, I think my first day as an assistant professor that shot was, so that was great to see. Okay, well, I'm not only did I do my education here, but I also grew up in Southern California. So I have this project to me resonated on a lot of levels. There were things about heat waves in Southern California that I experienced, but I didn't really understand. And I was really curious as sort of the efforts now with climate downscaling is how are things going to change for us in the Southern California region, and particularly in San Diego County. So I'll tell you a little bit about this SoCal Heat Hub that we've started, and then focus on two types of heat waves, the winter Santa Ana wind events, and the summer heat events, which I'm going to try and show you have something to do with the offshore ocean, which maybe wasn't fully appreciated. And then talk a little bit about adaptation strategies, mostly through ecohydrology and sustainable greening. So the problem was highlighted recently by the Los Angeles Times.
Excuse me, Mark, we can see your slides and we can see your slide progression at the bottom of the screen. Are you in presentation mode? Are you intending to be in presentation mode?
Does that work?
Okay, much better. Thank you.
Okay. Yeah. Okay. Yeah. So this is a study or an article by the Los Angeles Times, I think it was a couple of years ago, and really reporting that the heat or deaths due to heat in California have been underreported and underappreciated, and might be as much as 6 times higher than the official count. So you can see on the upper left-hand plot there, the gray line is what is reported as a heat wave fatality, and then the red is what's been estimated going back through hospital records. In either case, it does represent the deadliest consequence of climate change. It is the #1 cause of mortality based on these climate variability. And so the problem has really come to a head, as you can see here, since in the last decade, where the rate has really increased in the California region. Looking across the state, the number of deaths per 100,000 residents projected coming up in 2040, 2060, you can see how the southern part of the state, in particular San Diego, is in a real danger zone. And that goes hand in hand with the records we see every year, that every year turns out to be the hottest year ever. And last year was certainly the case. 2023 was much hotter than any other time. You can see that spatially the whole globe looks fairly red, much warmer, particularly over the northern part of North America. San Diego actually was not as bad during that particular year, but it has been creeping up. And on the right-hand side of the slide, sort of a startling look at, this is now daily global temperatures averaged over the planet, but just seeing how the histogram of temperatures has changed since 1940, where basically for 30 years or so, temperatures were fairly stable over the globe. There's a shift that happened in the late 1970s, which has been called the climate shift. And since then, the rates have been steadily going up, and now our minima, globally speaking, are higher than the maxima that we had in the middle of the last century. And for California, the projections are scary. So this is a look at taking the observed record, 1952, and this went up to 2015 with this study, looking at heat waves either as expressed as a daytime high or a nighttime high, and even the mix of that, the polarity of that has been shifting over time. We're seeing more nighttime hot conditions. But tying that to a global climate model, even under mild emission scenarios, and we will be seeing quite a few more heating days, heat wave days by the middle of the century, and then by 2100, it'll go up dramatically. So heat is with us, and we are going to have to contend with it more and more as time goes on. Scripps has been active for quite some time in the study of global warming and heating. And these are just some highlights headlines from some of the scientists in our heat lab. So these are the kind of work that they've been doing and how it's been expressed in the popular press. But in general, and to sum it up, Southern California extreme heat is a coastlines and people issue. It kind of depends on where you live, which raises the point that it's an environmental justice issue, and of course, it's a climate change issue. So that brings up the Southern California Heat Hub. This is a National Science Foundation 5-year funded project under the Coastlines and People program. And our hub was awarded, focused on the topic of extreme heat and its impacts in the coastal zone and ways to promote sustainable adaptation. So 5 years, we're just getting into it. It's ending in 2027. And we have a growing team involved in this. And generally, loosely speaking, the hub is organized in the right-hand diagram there, where we have 3 focus areas, sort of research focus areas, looking at the dynamics of heat from both from atmosphere, land, and ocean perspectives and how they interact. We're looking at, from a public health perspective, the epidemiology and environmental justice issues, and then this ecohydrology piece, the sustainable greening, which I'll tell you a little bit about. And these are all embedded within active units that are working to extend and broaden our education reach and also community engagement. From the climate dynamics theme, we're looking to explore how the ocean, atmosphere, and land drive and or modulate extreme heat across varied coastal zones and what changes are expected with climate change, some of our leads in that area. The health impacts and environmental justice, what are the locally specific health impacts of extreme heat and how do they vary according to land use and socioeconomic factors? Tariq Ben-Marnia, who's really one of our, who is a joint faculty between Scripps and Upper Campus Med School. And ecohydrology and greening, what is the locally specific relationship between temperature and vegetation, and where and how can vegetation be used for heat adaptation, and what are the associated climate water resource constraints? So it's fine to think we're going to improve greening by planting a lot of trees, but Southern California, can we really support that sort of endeavor with our water constraints? That's Morgan Levy. I'll loop back at the end on our education team and our community engagement team, but they're quite active, and we have many partners in these areas, particularly University of San Diego School of Leadership and Education Sciences. So our overarching goals: advance science knowledge and fill knowledge gaps in several fields. So provide government agencies, non-NGOs, and partners with science-based planning information. Aid in the assessment of existing urban planning efforts and future greening efforts with respect to climate change, health, and long-term sustainability. We're working with students, particularly from hard-hit communities, to expand curricula and opportunities. We're looking to that the hub is here to stay. We hope we're trying to build lasting partnerships between academia and the community that will endure. And we hope that this is a model for other coastal areas facing similar challenges. Okay, so that's the hub, and let's get right to the main science now. So this is looking at Santa Ana wind events. And as we all know, it gets warm here in the winter, the fall winter, when we get into a Santa Ana wind condition. And on the right-hand side highlights the other threat that happens with Santa Ana winds is they're often combined with wildfires. And so not only is it hot, it's dry. It's at a time of year when the combination of wind and dry lead to fire weather. They tend to happen primarily in the peak of winter, so sort of the December range. And if you track these over time, going back to the 1940s, quite a bit of year-to-year variability with just climate variability, but also you can see that there's a bit of a trend over time. So these Santa Ana wind events, particularly the extreme events, have been increasing over time. What are they? So there's a high pressure over the Great Basin in the winter, which leads to a pressure gradient. If you follow this track here going from Utah down to Southern California, that cross-section is here along the bottom of the screen. And the cold air under that high pressure in the Great Basin, there's a pressure gradient that air wants to go from high to low. So there's a low pressure off the coast. And that cold, dry air, as it flows across our terrain, when it hits our coastal mountain ranges, it descends. And as it descends, the pressure increases and the temperature increases. So what we get is very warm air that has been thermodynamically warmed as by these downslope winds. That is very, very dry, hasn't touched the ocean, is bereft of moisture. So what that looks like imprinted on our area, if we look at San Diego here on the middle panel, this is typical conditions during a Santa Ana wind event. And so you can see that the whole coastal zone, so this is, again, the warming happens in the lee of the mountains. So in the whole coastal plain of Southern California, we get this extreme heating associated with these events. The winds are all blowing offshore. And the kind of that dark area there represents the coastal zone for which our particular climate zone is defined primarily by these Santa Ana wind events. And again, showing that the events are increasing, not only the warming is happening during non-SAW days as well, but during SAW days, it's also going up. Okay, so this is some work by one of our researchers, Kristen Gurgis. And I guess the question she's looking at is the predictability of Santa Ana wind events. How well can we anticipate them, not only for short-term forecasts, but can we do a sub-seasonal to seasonal forecast of conditions that are likely to promote Santa Ana wind events? And with that sort of knowledge, can we then tie that to longer-term changes associated with climate change? So she was looking at this in the context of not only Santa Ana winds, but also atmospheric rivers, because the combination of these really dictate our susceptibility to fire in the fall, winter seasons, right? The lack of rain because we've had too few atmospheric rivers and which deliver much of the moisture or the rain to Southern California in a few events that kind of make up our yearly budget. And how many Santa Ana wind events are we going to have? So this is new to me, which I didn't understand. I didn't think that the atmosphere acted so kind of mechanistically, or at least statistically it does. And the premise is that you can define in the left-hand panel here 4 North Pacific modes that have characteristic atmospheric pressure fields, and or these are higher level geopotential fields. But basically, they're telling you kind of the surface weather patterns. And these are so iconic and so characteristic for our regions that each of these has a name. There's the Baja Pacific, where the center of action is sort of Baja California, Aleutian Low with the Alaskan Pacific mode. There's a dipole between the North Pacific and Canada with the Canadian Pacific mode. And then offshore of California, we can have higher low pressure that strongly influences our region. In the middle panel here, it shows how these 4 basic modes can beat together over the course of a year. So this is kind of tracking how, if you were to break up the atmospheric evolution during this particular season, how would these 4 modes be behaving? These 4 tracks track how that happens. So it's not one mode happening and dominating all at once. All 4 modes can be happening, and together they explain the progression of the atmosphere over this part of the world. And interesting, you can then statistically tie to the kind of the beating of these 4 modes. Also, the 16 weather patterns, which make up a surprising amount of, or account for a surprising amount of the variability, or just the basic weather we have over the western states and San Diego. So if you can kind of plug into these weather patterns and use these large-scale modes to drive the weather patterns, then this paper is showing that you have links to the way that AR make landfall, these atmospheric rivers make landfall, how much rain we get in California, the propensity for damaging floods, the snowpack in the Sierra, surface temperatures, Santa Ana winds, California wildfires are all dancing around with these modes. And together, this is kind of a weather model, but writ large and not taking into account very broad scales. So with each one of these 16 weather patterns, there is a precipitation anomaly associated. What are these rain events or non-rain events? So you can see weather patterns 7 and 8, high rain in the Pacific Northwest, 11, high rain in Southern California and over the Southwest. And then in the middle pattern, which of these weather patterns have associated with them Santa Ana wind conditions? So the first 6 are strong Santa Ana wind, are strongly related to Santa Ana wind events. And also at the bottom are temperature anomalies. So this is the surface temperature, the heat waves that we'll also be tracking. So depending on which latitude you are, will dictate how much of these weather patterns you see. So down in the Southern California region, about 30 degrees or so, you see a combination, our particular DNA, I guess, of weather that are corresponding to these weather patterns. Okay, so let's look at a particular Santa Ana wind event and see how this might work, or I think this is looking at a few of them. 3 Santa Ana wind events. This is when they occurred. When they occurred, this is what the modes were doing. The 4 modes were high or low. With this weighting, you would add all those together to get the weather patterns, and this is the characteristic weather pattern that you get. So this is the Santa Ana winds, which are swirling around this high pressure and coming off the Southern California region, causing the event. So with that, then Kristen is able to not only look ahead to a particular season to see whether, like in this El Nino year, are we likely to get more Santa Ana wind events or not? And also, it adds context to why these events are tracking over time. So we're seeing she's able to track not only which of these weather patterns are trending, but how they contribute to the increase in Santa Ana wind events. And in short, then, the combination of increasing Santa Ana winds, which are leading to these dry, hot conditions, and the reduction in wet conditions over Southern California, so that the drought that's been persisting and growing over time is responsible for the increase in fire weather for Southern California. Okay, so that is Santa Ana winds. This is typically what we care about in the winter, fall, winter months, and these are the events that affect the whole Southern California zone. What about in the summer? So we don't have Southern California events or Santa Ana wind events in the summer. The atmospheric pressures gradient isn't set up that way. And instead, we tend to get breeze from the ocean onto land. So the warming of the air over the land, particularly over the low mountains, causes the air to rise. That rising air is drawing in wind from the ocean. So we tend to get a ventilated, balmy Mediterranean climate in the summer, which really highlights why this is such a popular place to live. So what happens when the ocean is warmer than usual, and particularly what happens in the middle of what's called a marine heat wave? And that's depicted here. This was the 2019 heat wave. And just backing up a bit, in general, we know that the ocean is warming because we're measuring it directly using floats that were developed at Scripps. So on the upper right here is a cartoon of the Argo float, which tends to drift 9 days or so at about 1 kilometer below the surface. It does the descent down to 2 kilometers below the surface, rises. As it rises, it's measuring the temperature, pressure, and salinity of the water column. That information is relayed back to data centers by satellite, and the float sinks to 1 kilometer, and the cycle repeats itself. So every 10 days or so, we get a measure of where this float has drifted and what the ocean profile looks like. Enough of these have been deployed that we actually can do a global average of what the global ocean temperature has been doing. And sort of the alarming outcome of that is that we can see that if you average all those floats together, this is now a global average going from the surface down to 2 kilometers below the surface. The color is the anomalous temperature. So cool at the beginning of this, of the Argo phase. And over the 20-year period now, the whole column down to 2 kilometers is warmed. And in particular, the upper ocean has warmed considerably. That is causing that sort of all that increases leading to a rise in all boats sort of thing, where every now marine warm event has a tendency to become an extreme event as the mean increases. So this is what 2 of those look like in 2014. The warm waters were not just off of Southern California, but extended over the whole Northeast Pacific in what was called the blob. It just sort of hung around for a full season and led to all sorts of weather perturbations along the Pacific Northwest. 2019, there was another one that had more of sort of a horseshoe shape, but was really intensified off of the California region. So as the water warms, these heat waves warm. So if you measure a heat wave as being above some threshold, then the number of those heat wave events has been growing steadily over time and is rising in our region as well. That has a lot of impact on our local ecosystems, because when the water warms, it tends to cause the upper layer to be more isolated from the lower layer. The lower layer is the cold, nutrient-rich zone. So as you increase the stratification by warming the upper ocean, there are going to be organisms that can adapt to this and organisms that can't. And so this was a census of which of those are at risk, which are can find some benefit as these conditions persist. We also see what's called the tropicalization, where we see organisms that ordinarily would be found only off of Baja California or southern regions that are suddenly making their way all the way up to the Southern California region. And those are on the heels of these hot, warm marine wave, heat wave events. Okay, so does it matter that the ocean is a bit warmer or colder offshore? This is taking the maximum daily temperature in the during the day and averaging that for the whole summer. So we're really focusing on conditions that lead to warm events in the summer. So year to year, what is the average daytime temperature in the heat of the day? That variability, that temperature tends to have 2 dominant modes of variability, or they're kind of like 2 patterns that emerge that really define 2 separate regions. And not surprisingly, if you're sort of in the mountain range, and particularly as you head out into the high desert, that's one region that kind of beats together. So wherever you see color here is a high amplitude, high percent of the variability at these locations is explained by temperature changes that are associated with the time series above it. And what stands out here is just this blue zone along the coast. So this is symbolizing that the coastal zone is really independent of the inland zone. And so the Great Link, which the Santa Ana winds provide, are not there in the summer, and we're really buffered from what's happening in the desert region. So the coastal zone is behaving differently. And how it's behaving is on the right-hand side. So again, the bottom is showing the percent of variability explained in any particular location. Coastal zone lights up now. So now this is how the coastal area beats summer to summer. And that has really nothing to do with what's happening in the desert region. And that, what we're calling mode 2 here, or the coastal mode, is showed above. And again, these are, this is a summer, which is almost one degree warmer than usual, a summer that's getting down to almost 2 degrees cooler than usual. So what causes that variation from year to year? So looking at things that correlate with it, we see that the land temperatures correlate with the ocean temperatures, which is what we were kind of hoping to see, or suspecting that was the hypothesis, that as the ocean warms, so does the land, so does that coastal strip. And it's not just the temperatures, it's also how much clouds are offshore. So we're particularly used to this during the May gray, June gloom sort of thing, where these coastal low clouds develop and can really lower temperatures, and that the preponderance of those clouds really are tied to the coastal mode. And also the wind speed. So the winds off of Baja California seem to have something to do with this, and we'll get to that in a little bit. The remarkable thing about this is that if you look at this coastal mode, so this is the black line here. So this is the average temperature over all of Southern California. And it is highly correlated. You can see it's overlaid against the Scripps pier temperature. So if you measure the temperature off the pier here, you basically can tell how warm or cold any particular summer is going to be along the coastal strip. And again, just highlighting the strong link between the heat that's absorbed and stored in the ocean. The water has a high heat capacity. So once that heat is there, it tends to want to stay there. And that acts as a kind of a heat capacitor for the Southern California region. Going back in time, because the Scripps temperature record goes back, we can get a glimpse of what heat wave variability or summer heating looked like going all the way back to the early part of the 20th century. This is just showing kind of where the center of all this is happening. So on the upper left are the mean conditions in the summer. So what we typically see in the summer is the offshore winds are blowing north to south. The cool water that's coming down with the California current is flowing along the California coast and is warming as you get further south. What happens when it is warmer than usual is that we get an anomalous wind to the north, which means that these winds are basically dying out when you add this mean wind with this anomalous wind. And the ocean's getting warmer. And this is happening primarily off Baja California, and it kind of making its way or also influencing us in Southern California. So this was a surprise to me and to our research. We didn't realize that there was such a connection between, first of all, the ocean and the land. I mean, anecdotally, it makes sense, but nobody had actually confirmed it with measurements. And then also highlighting the importance of Baja California, which is an interesting, raises some interesting issues about how that warm water makes its way north. And again, that's, I think, linked to some of these tropicalization or these unusually warm water organisms that come up as well. So why is the wind matter? So the take-home message is that when the wind dies over the ocean warms, and that warms the land as well. And that dying of the wind, when the winds are strong, you tend to lose a lot of heat from the ocean. It cools the ocean. And when you have a lot of winds, you typically don't have a lot of clouds. So there's a lot of penetration of the, so there's not a lot of blocking of the heat or trapping of the heat by the low clouds. When the winds die down, it leads to the ocean warms up. It's not losing heat through the transfer to the atmosphere. And the low cloud conditions tend to also trap the heat in the atmosphere in the ocean. The winds also do something or contribute to what's called upwelling and downwelling. So the winds are stronger than usual. Waters in Southern California tend to be pushed from the coast offshore, and they are replenished by waters from below, which are colder than usual. So this is an upwelling of water associated with strong winds to the south. When the winds are weaker and there's a bit of a north component, then that all reverses and we see warming. So summer, if you jump into the ocean, often you'll feel that the ocean is much colder than you expected. And you can get a drop in the temperature out here of nearly 10 degrees over the course of a couple of days. And that's really associated with these upwelling, downwelling features, which can really lead to dramatic changes in the coastal zone. All right, so just to wrap this up, this is that year-to-year variability with how much heat there is offshore and how that affects the land. This is the average temperature in the coastal area, coastal plains of Southern California. And that is tracking and is correlated with the number of heat wave days we see. So when we're in one of these high coastal warming summers, we see a lot higher number of extremely uncomfortable warm days. So the heat wave signal is strongly modulated by the ocean. The ramification of this for human health is that it depends then how close you are to the ocean. I mean, and that's no surprise, but the closer you are, the cooler the temperatures. And that is borne out in the health statistics as well, but in kind of surprising ways. So the heat illness, we might have expected the coastal zone denizens to have fared better off than those in the desert. But surprisingly, just the opposite. The risk factor kind of went up in the coastal zone. And this paper is concluding that unusual heating actually affects people who aren't expecting it more than it does people who are prepared for it. So some of the ill effects of heating, surprisingly, are happening closer to the coast than we expect. And there are some implications about how people can respond to that, what's called the AC penetration. So how many people, what percentage of households have air conditioning? Not surprising that increases as you go inland, but it also varies with socioeconomic conditions. And so there are parts of San Diego that are, in a sense, more susceptible to heat waves just simply because they have no respite through an air conditioning or a cooling mechanism. Okay, what can we do about all of this? So that's sort of the big question is what can we, what sort of steps can be taken to mitigate these particularly heat wave conditions? And this is the work by graduate student Lady Wicker, Professor Morgan Levy, and Dan Can, Ecohydrology and Sustainable Greening. So they're looking at the interactions between hydrological and biological processes, the way plants use water, wetland ecology, the whole water cycle, role of water in the carbon cycle, and how these play through toward to actually affect humans. So the kind of questions they're looking at, what kinds and amounts of vegetation correspond to health impact relevant change in temperature? Is water and water infrastructure available to sustain desirable levels of urban greening? And what challenges or benefits does projected coastal climate pose for vegetation and urban greening? What do climate resilient and water sustainable urban greening plans look like in San Diego? And they're asking these questions because green space can be modified locally. It is a lever for adapting to the heat exposure risks of climate change. And anecdotally and in our everyday lives, we're well aware that green spaces are cooler, but we have limited sort of large scale understanding of how urban vegetation and other environmental features, particularly the built environment in the urban zones, interact to lead to cooling locally or not. And why San Diego? A lot of environmental diversity, which makes the region a good case study from like a purely scientific perspective, a lot of different terrain. And the socioeconomic diversity, which makes the region a good case study from an equity and impacts perspective. So they're investigating the interaction between temperature extremes, land cover, and water use. And so the motivation is that if you understand how water is consumed in regions of variable plant cover reacts to extreme heat, we can better predict what water consumption will look like as the landscape changes and urban greening efforts evolve. So really trying to tie water consumption to heating and how that eventually will impact the way we can do greening, depending on our water use tendencies. So they start out with these hypotheses that agency level water deliveries will be sensitive to temperature extremes, and sensitivity will depend on land cover, coastal proximity, and precipitation and humidity. So this is the sort of data they've been looking at, which is overplotted on each other versus the day of the year. The green curve is the daily maximum temperature. The blue curve is the daily water delivery, how much water is being used. And you can see that obviously the seasons, the summer season in the middle of the plot, and the water use that tracks that. So basically, hotter it is, the more water that is being used. That, if you plot that as a scatter plot, so the x-axis is the temperature, the y-axis is the water you're using, then that relationship varies. The sensitivity of temperature and how much water is needed in a particular zone can vary from place to place, depending on the water district. So the steeper these curves, the more water that area needs for a given temperature increase than other places. And you can see quite a bit of variability there. So how do they characterize this variability? So that's shown here. That's the slope of those curves is essentially a kind of like a trend rate is shown here. And as that sensitivity, or as the water usage for a given temperature increases, so these are the areas that use a lot of water for a given increase. These are the ones that don't use a lot of water. Those really track how much cultivated, sort of the percentage of managed land in that particular water district. So the more managed, or the more built by farms, parks, golf courses, the more demand there is from that sense, the more the water usage goes up. Again, maybe not surprising, but nice to quantify it and to actually get numbers associated with it that you can use in a planning context. So two examples here: Sweetwater, a very open area without a lot of development, uses very little water for even normalized by population. And Valley Center, on the other hand, with a lot of farming, a lot of recreation use, the usage goes way up. This is true not only for the mean, but also for variability for extreme cases. So when it gets to be extremely hot, there's extremely a lot of water use. And that also can be tracked to the amount of, in this case, the amount of agriculture in the region. So the hotter it is, the more water is being consumed by agriculture to in these managed environments to account for it. So this is a model that they're putting together to try and understand water use patterns. And with it, then what happens if we start to add a lot of greening and a lot of demands in terms of keeping green space green? And can the water system actually account for, keep up with it, particularly given trends that we're seeing in reductions in rain, more drought conditions, less snowpack, and more challenges for the water supply for Southern California. So green space is an obvious benefit in hot conditions, but the maintenance of green space is going to be an issue going forward. Okay, just to flip away from some of the projects and more just generally about the hub, we're trying to work with communities. And so one community partner that's been particularly sort of has been very beneficial for us to get their experience and their kind of network involved is what's called the Earth Lab. They have a laboratory space, a green space that's connected with an Encanto right in the middle of a very urban environment with lots of a variety of vegetation. There's a stream bed that runs through this area. So we're testing some of the greening strategies in the Earth Lab and working with local students and community members to develop these projects. And so we're working with Fauna Foreman and Teddy Cruz. We have a lot of outreach to schools. So we've been installing weather stations at schools to give them hands-on look at how the temperature and how the conditions are changing on their campus. And with that, we're trying to build a system that creates data that, particularly the middle grades and high school level, that we can build curricula around, how to use that data, how do you analyze that data. Also trying to build out connections between the schools. So we do intercomparisons, or can students get together to see how their conditions might vary compared to other schools across the Southland. So these weather stations are going, there's one on the left here, which is measuring temperature, winds, humidity, and whatnot. We're also doing thermal mapping of schools. We're doing it on the ground, but also in the air with drones, with ultraviolet cameras. So we're trying to understand these urban hotspots, urban hot zones. These are not surface temperatures, but this is the amount of thermal radiation, infrared radiation that's being radiated from hot zones. And so we're trying to relate how these hot areas are distributed, how hot it actually gets. So how do we relate these infrared measurements to actually temperatures on the ground? We're also building a lot of curriculum in terms of just how to build gizmos and sensors that you might want to use to measure different aspects of your environment, and particularly how hot it's getting. We're working with the kind of data sets that we tend to use at Scripps, which are more satellite data, in situ data from buoys and ocean sensors around the Southland. How to take advantage, how to access that information, how to use it, and understand what can be done in terms of projections. And also just developing curricular experiments to highlight the physics and some of the chemistry and whatnot associated with heating, and how simple desktop experiments can lead to insights about what our area is doing. This is our team. If anyone's interested in becoming more involved in the education piece, we have a very strong team led out of the Birch Aquarium. And I guess I just wanted to leave with this hot heat map. This is what motivates us, is that this is the same thing we're seeing on the school ground. This is what you see from a satellite for all of Southern California, and everywhere it's yellow there has an extremely hot land temperature. And where it gets darker, it's cool, and you can see El Cajon Boulevard, you can see freeways, you can see the canyons, and there's a lot of natural and built variation terrain that leads to variations in how people experience heat. We're trying to give them more information that they can use on a very local scale, even at this level, and also trying to develop some strategies for how they might want to get some relief from this heat. And with that, I will be happy to answer any questions.
Wonderful. Thank you